Okay, still in section 3.4, and we're still talking about motion along a straight line. And so we just went through on our last example an understanding of acceleration versus velocity, and we saw that acceleration is the first derivative of velocity, which, by the way, means it's the second derivative of position. Okay? Now this concept of jerk is the derivative of acceleration, or the third derivative of position. But if you think about what that means, the derivative of acceleration is how is the acceleration itself changing? And that's called jerk because if you think about it, it's kind of like if you sit in a car and I don't know, somebody's learning how to drive a car, early on and they're using a stick shift, so they do a lot of jerking. Well, that's actually where it comes from. Your acceleration is changing pretty rapidly because you jerk the car. So if you jerk the car, that's the derivative of acceleration. We won't really use that much. I just wanted you to understand in physical terms, there's an understanding of what the third derivative of position is. It's the derivative of acceleration because acceleration is the second derivative of position, and the derivative of acceleration is actually what we call jerk. Okay, but let's go back and use all of our relationships now. So in this example 38, the figure to the left shows the free fall of a ball bearing released from rest at time t equals 0. So I'm standing up here, or I'm up on a tower or something. I'm actually going to call the top of that tower position 0. So when I drop a ball just out of my hand, drop a ball bearing, it's going to fall due to gravity, right? Okay, so notice I always have to figure out what is my s-axis, what is my position axis. Okay, and I have to know where 0 is so I know whether velocity is positive or negative and those kinds of things, all right? So when I set this position 0 at the top of the tower, then if I drop the ball, it's going to be positively going down. So down is actually positive when I do this. Hopefully, or maybe you don't remember, I don't know, but from high school physics or something, Galileo came up with an understanding of free fall. And he understood that the position of anything that falls freely is represented by this function of time. It's 1/2 gt squared, where g is the gravitational constant. It's all due to gravity. So if we're talking about meters, notice the thing we're talking in meters here, then that gravitational constant is 9.8 meters per second squared. If we were talking about feet, it's 32 feet per second squared. And those are typically the only two units we're using. So in this case, we're using meters, so it's g is 9.8. So the bottom line is the position s of this ball bearing at any time t will be this simplified, which is 4.9 t squared. Okay, so we have to know that to start off with. Now to answer the questions, how many meters does the ball fall in the first 3 seconds? That's asking you what is its position at t equals 3 seconds. That's just saying what is s of 3. You plug in 3, you get 4.9 times 3 squared, that's at 44.1 meters, and you can kind of see at t equals 3, that's where the ball bearing is, right around 44.1. And then it says, what's its velocity, speed, and acceleration when t equals 3 seconds? So before we do it, think about it. Velocity is still going to be going down. It's going to be a positive velocity. Should be pretty fast after 3 seconds, right? The acceleration is going to be speeding up because gravity is going to make it speed up, right? So acceleration is going to be positive as well since velocity is positive. And anyways, we'll just figure that out. So v of t, the velocity, is the derivative of position. So the derivative of position is just this simple power rule here with a constant multiple in front of it. So you leave the 4.9 alone, take the derivative of t squared, get 2t, so it's 9.8t. That's the velocity at any time t. So what's the velocity at time 3? You plug in t equals 3, and you get 29.4 meters per second. So the speed is just the absolute value of that, but it's positive, it's the same value, 29.4 meters per second. And then the acceleration is just the derivative of velocity. So once we have velocity at 9.8 t, the derivative of velocity. Also want to keep reminding you it's the second derivative of position, but most of the time we think of it as derivative of velocity is 9.8, which makes sense. That's the gravitational constant. That's how we came up with what the function is, where it is at any time t is by this gravitational constant. So it's 9.8, sorry. So acceleration at time 3, acceleration is always the same. You only accelerate due to gravity, so it's 9.8 meters per second squared.